Okay, so let's find t. So t one more time is equal to r prime over the norm of r prime. Okay, so r prime is equal to the derivative of each of these here. Be careful, check of the product rule. So it's derivative of e of t is e of t. By the product rule, derivative of e of t is e of t sine of t plus e of t cosine of t. And then the derivative of the third component, e to power t cosine of t minus e to power t sine of t. Okay, now what we want, can I write this in a slightly better form? Well, only if I factor for these two e to power t sine of t plus cosine of t, and same here, cosine of t minus sine of t. Okay, now the magnitude of this factor is equal to the square root of the sum of the squares of each of these components. So that's e to power t squared plus e to power t sine of t plus cosine of t squared plus e to power t cosine of t minus sine of t squared. Okay, which is equal to square root of e to power 2t plus e to power 2t sine of t plus cosine of t squared plus e to power 2t cosine of t minus sine of t squared. Okay, which is equal to square root of e to power 2t plus, I factor e to power 2t for these two. I could have included this one also, but let's start with this two. So I square this part, that sine squared t plus 2 times sine of t cosine of t plus cosine squared of t plus, and then I square this part, cosine squared of t minus 2 times sine t cosine of t plus sine squared t. Okay, so obviously these two terms go away. Okay, and then we have sine squared plus cosine squared is 1, and cosine squared plus sine squared is 1. So 1 plus 1 is equal to 2. Okay, brings us to that r prime of t is equal to square root of e to power 2t plus, so one more time, these two terms cancel. Sine squared plus cosine squared is 1. Cosine squared plus sine squared is 1. 1 plus 1 is 2. So here I have 2 times e to power 2t, which is equal to square root of 3 e to power 2t. And I can evaluate this square root e to power t times square root of 3. Okay, please stop me whenever you have any questions. Now, the unit tangent vector at any number is equal to, r prime of t over its magnitude is equal to, the magnitude is e to power t square root of 3 times r prime of t was e to power t sine t plus cosine of t e to power t cosine of t minus sine of t. Okay, this is a this term can go inside the vector, and I get also, if you want me to speed up a little bit, I'll gladly do that. This is literally, I'm going here step by step. But that's not bad, because if I make a mistake in such a big problem, then I won't know how to come back. And then cancel this, and you get not that only the constant here, so that's 1 over square root of 3, 1 sine of t plus cosine of t, and cosine of t minus sine of t. So that's the unit tangent vector, okay? Any questions? Now let us find the normal vector. The normal vector is the derivative of the unit tangent vector over its norm, okay? So the derivative of the unit tangent vector is 1 over square root of 3, right? That's a constant, times derivative of 1, 0. Derivative of sine plus cosine is cosine of t minus sine of t. And this one is negative sine of t minus cosine of t. Okay, so the norm of this vector is equal to square root of 0 squared is 0. So cosine of t minus sine of t over square root of 3 squared plus negative, I factor negative here, sine of t plus cosine of t over square root of 3 squared. Okay, which is equal to, I'm not gonna have space to continue here. T prime of t is equal to the square root of cosine squared t minus 2 times cosine t sine t plus sine squared of t plus negative 1 squared is 1, so you just have sine of t plus cosine of t squared, and that's sine squared t plus 2 times sine t cosine t plus cosine squared of t. All that divided by 3, right? Okay, again, we have these terms to cancel. So t prime, the magnitude of t prime is equal to square root of cosine squared plus sine squared is 1, sine squared plus cosine squared is 1, 1 plus 1 is 2 over 3. Okay? In that case, the normal vector n of t is equal to, again, I'm just going to write the formula. Derivative of the unit tangent vector over its norm. The derivative of the unit tangent vector was 1 over square root of 3, 0, cosine of t minus sine of t, negative sine of t minus cosine of t over square root of 2 over square root of 3, right? And then we cancel these two. 1 over square root of 2, 0, cosine of t minus sine of t, negative sine of t minus cosine of t. And this is the normal vector. Now, for a second, I forgot what I was looking for. Okay. So we have found the unit tangent vector, we have found the normal vector, and now we have to find the binormal vector evaluated at pi over 2. Now, of course, I'm not gonna find, I can evaluate the cross product of the general unit tangent vector and the normal vector, but this question has been a little bit nicer to us, and they ask us the binormal vector at pi over 2. So that's the unit tangent vector at pi over 2, cross product the normal vector at pi over 2. Okay, so this is the unit tangent vector, right? So how much is going to be the unit tangent vector at pi over 2? That's 1 over square root of 3. 1 is just a constant. Sine of pi over 2 is 1 plus 0 is 0. And cosine of pi over 2 is 0 minus 1. Okay. So that's 1 over square root of 3, 1 over square root of 3, negative 1 over square root of 3, cross product. Now the normal vector at pi over 2 is equal to 1 over square root of 2, oops, sorry, 0, negative 1, and here again, negative 1. So 0, negative 1 over square root of 2, negative 1 over square root of 2. Okay, so let's find this cross product. Is equal to I. So what do we have here? I have 1 over, let's put it like this, negative 1 over square root of 6 minus positive 1 over square root of 6. I minus, this is negative 1 over square root of 6 minus 0, j, plus this is a negative 1 over square root of 6 minus this is 0, k. So this is equal to negative 2 over square root of 6. Negative times negative is positive 1 over square root of 6, and negative 1 over square root of 6, or that's equal to 1 over square root of 6. Negative 2, 1, negative 1. Okay, the binormal vector at evaluated at pi over 2. Any questions, guys? Question part B. Find the length of the curve from the point A, which is 101, to the point B, which is E times sine of 1, E times cosine of 1. Okay. Right, so the first thing that I remember that the length, the arc length is equal to the definite interval in terms of t, right? So that means I have to find how much is t. So in order to do that, recall that r of t is equal to e to power t, e to power t sine of t, e to power t cosine of t, and then find a way to identify how much is this. So t is 1, oops, sorry, t is 1, t is 1, okay? So obviously t is less or equal to 1, e to power 1 is e, okay? And on the other hand here, e to what power is 1? E to power 0. If I had put here 0, the sine of 0 is 0 times 1 is 1. So t runs from 0 to 1, okay? That means that the arc length is evaluated from 0 to 1. Okay? Now we have evaluated this. And this, if you go back in the notes, you will see that is equal to square root of 3 times e to power t dt. So you see, this is now quite simple. We've done the difficult work. We evaluated this previously. So that's square root of 3 e to power t evaluated from 0 to 1, which is square root of 3 e minus 1, right? E to power 1 is e to power 0 is 1. Any questions? And then you have C. In C, we say what is valid, find the curvature. Find the curvature of C. That means at any point here you have to decide, right? If the question is just find the curvature without addressing the unit tangent vector, the normal vector, then you go find the first derivative, find the second derivative, and find the cross product. But if you already find the t prime and its magnitude and r prime and its magnitude, then it's much easier to use this formula. So this right here, again, you have to put in your notes. It's square root of 2 over square root of 3 over this is square root of 3 e to the power of t. So this is just square root of 2 e to the power negative t. Any questions? Okay, so now let's address the normal and the osculating plane. Find the normal plane and the osculating plane of C at pi is equal to t over 2. Okay, so I don't know if you guys figured it out what what I tried to say yesterday. So we have some kind of curve right here. The plane that hits this curve right here, right, goes through the plane. It's called the normal plane, right? Because the tangent vector, the unit tangent vector is going to be here at this particular point. Let's say it can go here. So the unit tangent vector is orthogonal to this plane, right? So when we're looking for the normal plane, we just have to solve t dot product r minus r naught is equal to 0, where r naught is equal to r at pi over 2 because of the question, and that is equal to e to power pi over 2 0, no, sorry, e to power pi over 2, e to power pi over 2, and then 0, right? That's the point, because one more time, r is equal to e to power t, e to power t sine of t, e to power t cosine of t. Okay, and how much is the unit tangent vector at pi over 2? The unit tangent vector at pi over 2 is equal to 1 over square root of 3, 1, 1, negative 1. Now look at this. If I just take the vector 1, 1, negative 1, that's going to differ by the what? By the length, right? It's basically going to be if I take the vector n being 1, 1, negative 1, that's this vector, right? But it's still that vector is orthogonal to the plane, so our calculation is going to be much easier, right? How do we find an equation of a plane? It's a vector normal to the plane, so any constant multiple times that vector is also going to be normal to the plane. So I'm just making the calculation easier. Nothing is going to change if you take this particular vector. But this is just a constant multiple of this one. So I take this vector. So it's the equation of the normal plane and dot product r minus r evaluated pi over 2, right? The point. So that's 1, 1, negative 1, dot product x minus e to power pi over 2, y minus e to power pi over 2, 0 is equal to 0. And this is just a dot product. 1 times e to power x minus e to power pi over 2 plus 1 times y minus e to power pi over 2. Negative 1 times 0 is 0 is equal to 0. So x plus y is equal to 2 times e to power pi over 2. The equation of the normal line, normal plane. And finally, the osculating plane. So going back to this picture, so here is going to be, let's say, this is going to be n, right? And there's a cross product is going to be here, which is going to result in b, right? Okay. So the osculating plane is the plane closest to the curve. Why? Because both t and n belong to that plane. T and n belong to that plane. So that means that the binormal vector is orthogonal to the osculating plane. So B is orthogonal to the osculating plane. So that means that its equation is B dot product x minus e to power pi over 2, right? Is the same point, y minus e to power pi over 2, 0 is equal to 0. And now this is, of course, the binormal vector at pi over 2. And the binormal vector at pi over 2, we evaluated somewhere. V evaluated at pi over 2 is negative 2 over square root of 6, 1 over square root of 6, negative 1 over square root of 6. Again, I can take any vector, that's a constant multiple of this vector, and I'll have the same, I'll have a normal vector to that plane. So I take, let's say, n1 to be my vector, negative 2, 1, negative 1. So the equation of the osculating plane is negative 2, 1, negative 1, dot product x minus e to power pi over 2, y minus e to power pi over 2, 0 is equal to 0. So here you have negative 2x minus 2 e to power pi over 2, sorry, plus y minus e to power pi over 2 is equal to 0. Negative 1 times 0 is 0, so you get negative 2x plus y is equal to negative e to power pi over 2. Any questions, guys? And finally, yes.
It's not a question, but I just wanted to let you know that you have like this 6 minutes remaining. So I don't know if you were planning on starting another thing. So it just doesn't cut even at all.
No, I'm gonna finish right here. No, of course I'm not just gonna cut out, but I'm gonna try to finish the problem here. The last question, because I'm recording this, so I want to try that. I want to upload the recording I want to check, and I want to finish in 6 minutes, if I can find, I don't know what part is this, determine on what surface this curve exists, on what surface this curve lies, right? So you have r of t is equal to e to power t, e to power t, sine of t, e to power t, cosine of t, okay? So let x be equal to e to the power of t, y being e to the power of t times sine of t becomes, becomes x times okay, okay, and y and z is equal to e to power t cosine of t, but from here look at this, y squared plus z squared is equal to e to power 2t sine squared t plus e to power 2t cosine squared t. So y squared plus z squared is equal to e to power 2t sine of 2t plus cosine of 2t, sorry, plus cosine squared of t. This is 1, so you get y squared plus z squared is equal to e to power 2t, and e to power t is x, so this is equal to x squared. So y squared plus z squared is equal to x squared, and we learned about this, the surfaces. This surface is called the cone. So this curve that we have been working on lives on this surface here, right? Centered at the origin, and that expands along the x-axis. Okay, so I'm going to stop this meeting right now, and then I'm gonna join in again because I have only 3 more minutes for some questions if you have, okay? So see you in a second.